Let us talk about evaluating the output of a linear regression model. Let's say you have built a model and you have made predictions. Now how do we evaluate whether your model is good or bad? So in this video we will talk about a few parameters which help us understand whether the model is performing well or it is not performing well. So let us start this with an analogy. So the analogy I will make is that of a student appearing in a test. A student appears in a test and he scores, let's say, 80 out of 100. Now how can we evaluate a student? We can evaluate the student on two ways. In two ways we can evaluate the students. The first way is looking at the 20 marks which he was unable to score. So looking at the 20 marks which he was unable to score, and the second way is looking at the 80 marks which he was able to score. So this will be looking at his strengths and this will be looking at his weaknesses. So in both ways we can evaluate how good or bad the student is. Similarly, in case of a model, there are two ways of evaluating a model. One way is checking the error the model is making, and the other is checking the accuracy of the model. How accurate is the model? So in both the ways we can evaluate the model. So let us first look at the parameters that are used to check the errors that the model makes. Let us look at that first. So the first parameter that we will be looking at, which measures the error a linear regression model is making, is called sum of squared error. So we have seen this before, sum of squared error. So what is the formula of sum of squared error? The formula we have seen before, it is actual minus predicted, which is the error, whole square, and you add all those values. So this gives you the sum of squared error. Now you might wonder, why are we not just adding up the errors? Why are we not just finding the sum of the errors? So we have answered this question before. In case of a linear regression, the sum of errors is always equal to 0. So if you add up all the errors, it will always be equal to 0, because a few errors will be positive, a few will be negative, and they will cancel each other. Hence we do not just take the sum of errors, we take the sum of squared errors. So we square each of the errors so that the sign gets eliminated, and then we add them up. So two models, if we have built two models, the model which has smaller value of sum of squared error usually is a better model. Now let us move to the second parameter. The second parameter that we use is called RMSE. So what does it stand for? It stands for root mean squared error. Now the first question which comes to our mind is, why do we need another parameter if we have sum of squared error? Now sum of squared error has a few disadvantages. Now what is the first disadvantage? The first disadvantage is the units are in squared. So if you are measuring, if your dependent variable, for example, is, let's say, dollars, if you're talking about income of a person or sales of a company, if your dependent variable is in dollars, the sum of squared errors will be in dollar square. Now dollar square is not interpretable, so this is one big disadvantage of sum of squared error, that it is not interpretable since it has squared units. Now the second disadvantage which sum of squared error has is that it depends on the number of data points you have included in your model. So imagine if somebody has built a model using only 3 points. If only 3 points he has included, or 3 rows, he will have 3 errors. So error 1 whole square, error 2 whole square, and error 3 whole square. This would be his total sum of squared error. Compare this with another person who has included 30 points into his model. So in his case the errors will be E1 square and it will go all the way till E30 whole square. Now of course this will have a higher value than the previous one because there are more points included here. But that doesn't mean that the second model is worse than the first model. It is only because it has more number of points, the value of sum of squared error will be higher, not because it is a bad model compared to the first one. So this is another disadvantage of taking sum of squared error, that if you have different number of points, it becomes difficult to make a comparison since sum of squared error depends on the number of points. So this depends on n. So these two disadvantages are there in sum of squared error. Now to the second parameter, root mean squared error. In this parameter we will try to get rid of both the disadvantages of sum of squared error. So let us see how can we remove those disadvantages. So to find the formula of sum of squared error, we can start from the right hand side. So what is the first word that you see? It is the error. So how do we calculate error? We do actual value minus what we predict. So actual minus predicted is the error. Next, the next word is squared. So I will square it. What is the next word? It is mean. So take the sum of it and then find the mean. So I divide it by n to find the mean, and then I take the root of it. So I take the root of the entire thing. This is my root mean squared error. So I can easily find the formula by starting from the right hand side and going towards the left. So this is the formula of root mean squared error. Now you see the first disadvantage that we had was of squared units in sum of squared error. Now here we are taking a square root so that the units are back into dollars. The units are no longer dollar square, it is back into dollars. So it is more interpretable. The second disadvantage of sum of squared error was that it depended on the value of n. So in this case what we are doing, we are dividing it by n so that it no longer depends on the value of n or the number of points included. So this way we can remove both the shortcomings of sum of squared error, and we have root mean squared error. This is also very popularly used to evaluate the accuracy of a linear regression model. Now moving to the third one. The third error parameter that we use is mean absolute percentage error. So mean absolute percentage error. Now why do we use this then? If we have removed both shortcomings of sum of squared error and we have root mean squared error, why do we need another one? Now root mean squared error also has one small disadvantage. Now that disadvantage is it gives us the value of error as a absolute value. So it will give us some number. So let's say 5, 10, whatever. It will give us some number as the error. But it becomes very difficult to interpret by an absolute number how big or how small is your error. So let's say for example your error is 5. Your root mean squared error is 5. Now what do you think? Is this a large error or is this a small error? Now that depends on what your actual value is. If your actual value is 4, then this error is small. But if your actual value is, let's say, 0.1, and then if the root mean squared error is 5, that means it is almost 50 times the actual value. So in this case it is a very bad model. But if your actual value is 4 or 3, and then if your RMSE is 5, that means it is almost a good model, I would say. It is a fair model because your actual value is 4 and your model is predicting 5 away from 4. So the RMSE means that you are 5 units away from the actual. So if your actual is 4, you are plus minus 5. In general, on an average, you are plus minus 5 units away. Similarly, if your actual value is 0.1, it means you are plus minus 5 units away. Now this would be a huge range. This would be a very bad error if you are 5 units away from an actual value of zero point 0.1. So this is where RMSE fails because it gives us an absolute value of error. It becomes very difficult to compare with the actual value, and it becomes difficult to judge sometimes whether the error is small or large. Hence in MAPE we review the error in terms of percentage. So in terms of percentage we will review the error now. So we will not get the error here as a absolute value, but we will get it as a relative value. So once again, to find the formula of MAPE, we start from the right hand side. So first is the error. So I will calculate actual minus predicted. Then we take the percentage. To take the percentage, I will divide it back by the actual value. Then I take the absolute. So let me take mod of it. And finally I take the mean. So I will take the mean here. I will divide by n. So in this case, we are removing the shortcoming of RMSE, which is that it gives a absolute value. So we are comparing it with respect to the actual. Hence what we get will be as a proportion of the actual. So in this case, for example, let's say we get 1. This means that, let's say we get 0.01. This means that your error is 1%. So if your actual value is 100, your model is predicting plus minus 1%. So 101 or maybe 99. So this means you have built a very good model which is just giving a 1% error. So it becomes very easy to understand and to interpret if you are reviewing your errors in terms of mean, absolute, percentage error. So these are the 3 error parameters which are very popularly used, each having its own advantage and disadvantage. Now coming to the accuracy side, let's come to the accuracy side and see what are the accuracy parameters that are used. So the accuracy parameter used in case of a linear regression, the first parameter that we will be looking at is called R-square, capital R square, which is also known as coefficient of determination. So what is R-square? Let us first look at the mathematical formula. The mathematical formula for R-square is 1 minus sum of squared error divided by total sum of square. Now what is sum of squared error? We have already seen what sum of squared error is. It is actual minus predicted whole square and sum of all of them, or in other words, it is the sum of all individual errors that we make. It is the sum of squares of all individual errors that we make. And what is TSS? Now TSS stands for total sum of squares. Now how do we calculate this? We calculate this by actual minus the average value of the dependent variable whole square. So this has the same formula as sum of squared error, the only difference being instead of writing the predicted value, we write the average value of the dependent variable. So y bar is average of dependent variable. Else it is the same as sum of squared error, but instead of writing the predicted value here, I have written the average of the dependent variable. So using this we calculate R square, which is the coefficient of determination. Now what is the interpretation of R square? What does it measure? Let us see. R square is a value between 0 and 1, with higher values representing a better model. So if you get plus 1 means it's the best model you could ever build. That means your values are all along a straight line. So your line is perfect and all the points lie on the line. In that case you will get a R square of plus 1. R square closer to 0 represents a not so good model or a very difficult data. Now what is the interpretation of R square? R square measures the proportion of variance captured by the model, measures in terms of proportion So it measures the proportion of variance or information captured by the model. So how much information present in the data has been captured by the model. So let's say if you get a R-square of 70% or 0.70, this means that 70% of information present in the data has been captured by the model. If you get a 90% R-square, it means 90% of the information in your data has been captured by the model. So the more information you capture, the better the model is. So this is how we define R-square. This R-square is also known as multiple R-square. This is also known as multiple R-square. So this is the interpretation of multiple R-square. The higher the value, the better it is. So finally, to conclude, how do we evaluate a linear regression model? So there are two ways to evaluate. One is looking at the error parameters. The other is looking at the accuracy parameters. So the error parameters that we saw is sum of squared error, so which has a disadvantage of the units being in squared and it depending on the values of n, the number of points taken. So we have some other parameters like root mean squared error, where we take the square root of the sum of squared errors so that we don't get squared units, and also we divide by n so that it doesn't depend on the number of points taken. But it suffers from the disadvantage that it always gives us an absolute value, and sometimes it becomes difficult to interpret if you have an absolute value. So we have mean absolute percentage error, which helps us understand the relative amount of an error with respect to the actual values. So this is as a proportion we get the error value in MAPE. So using the proportion we can estimate whether you are making 5% error or you are making 10% error. Of course, the smaller the values of these error parameters, the better the model is. Similarly, on the other side, we have the accuracy parameters, where the higher the value, the better it is. So the accuracy parameter that we saw is R-square. So R-square is known as coefficient of determination, which measures what proportion of information has been captured by the model. So the higher the value, the better it is. It can take a value between 0 and 1 since it measures proportion. So if you get closer to 1, it means you have captured most of the information present in the data. If you get a value closer to 0, it means you haven't captured enough information and your model is probably not a good model. We saw the formula to calculate R-square. It is 1 minus sum of squared error divided by total sum of squares. What is total sum of squares? Total sum of squares is the same as sum of squared error. The only difference being, instead of predicted values which come from a straight line, we have the average of the dependent variable. So here we have a constant which is the average of the dependent variable.